So I think we can just start.
Yeah. So just just 2 lines. This is the second lecture of Professor Vladan Vuletic, and this is also turns out to be the last lecture of the school. And tomorrow we'll be starting the discussion meeting, which is effectively structured in the form of a conference, very compact 2.5 days. So I welcome everyone to, on behalf of the organizers, to be there. And over to Vladan. I think you can start.
Thank you very much, Saikat. Okay, so as promised today, part 2, again focused on Rydberg interactions, but this time we are talking about, the system down here, where we're using the Rydberg interactions not to manipulate photons, but we shine in light, excite atoms to Rydberg states, and use them to realize interactions between atoms and spin models and quantum gates that I would like to tell you about. So preface, where is this all? What was this all enabled? It was enabled by a beautiful experiment performed by Philippe Granger, who managed to trap a single atom, and detect optically a single atom inside a laser beam. This is now basically 20 years ago. 2 decades ago, they used the vacuum chamber filled with a very dilute vapor of, rubidium, 780 of rubidium. They had a very good lens inside the vacuum, or very close to the atoms, with a high numerical aperture on the order of 0.5, 0.6 or so, to collect a lot of the fluorescence. And then basically they had the laser cooling and trapping beam, and the atom was shining light that was collected through the lens and through some spatial filtering onto a CCD camera. And also onto an avalanche photodiode, and this is what they saw on the camera. They basically or maybe clearer is the time trace here on the photon counter. So they either saw a low count rate, flat count rate of, in this case, 20 counts per 10 milliseconds, which corresponded to no atom being trapped, or a higher value, about 3 times higher value of photon counts, and this corresponded to 1 atom being trapped. And you can see that, the atom was, this is time in seconds, the atom was loaded into the trap, lost from the trap, loaded into the trap, etc., sometimes staying for quite a long time, several seconds. But very interestingly, they never saw twice this step. They never saw 2 atoms in the trap. And this was, quickly or understood at the time already. Basically, if you have 2 atoms very close to one another in such a tightly focused trap, this trap was less than a micrometer big. We call it optical tweezer nowadays. It was less than a micrometer big. It turns out that when you put atoms so close together on the order of a wavelength or less, then you can very easily excite 2 atoms to some kind of molecular potentials, to some molecular state where the atoms either dissociate and quickly both are lost from the trap because of the interaction energy of the molecule, or they are photoassociated into a bound state of the molecule, and this bound state of the molecule has different transition frequencies and is, basically invisible to the light and just leaves the trap. And so basically they showed that with a probability of about 50%, they could prepare and detect a single atom inside a trap. And then for a long time, this field was somewhat dormant. I mean, people performed experiments with just one atom per trap. And then Michael Lukin, Markus Greiner, and I, this idea, I should give full credit to Manuel Endres, who really pushed this idea, who was a postdoc at Harvard at the time. Here was an idea that we did then, is to turn this kind of, random loading of an atom half the time into a trap, into a deterministic loading of atoms into a trap. And pioneering work in this field has also been done in France by the group of Antoine Brouet, and by now, a number of groups are now using this. So here's what we did back in 2016. We had again a vacuum cell with a dilute rubidium vapor and laser cooling and trapping, basically MOT laser beams to cool the atoms. And then instead of doing a single trap, we use the so-called acousto-optic reflector. It's basically a sound wave at different frequencies traveling through this crystal, which leads to a deflection of the beam into multiple spots. So here shown are 3 spots, but we can make something like 100 spots in the system. These spots are focused in an intermediate plane on to foci with a good lens system. Here's a microscope objective. So in the end, inside this vacuum cell, we make something like 100 strongly focused trap. Again, the the size of the focus is maybe 0.9 micrometers or so. So very tightly focused laser beams. And then we image these atoms inside a trap onto cameras. Here we image both the traps themselves and then any atoms that would appear in these traps. And as already Rydberg had done, we could load atoms with 50% probability into these traps, between 50 and 70%. However, even though this is probabilistic, we can detect the individual loaded atoms very quickly via the fluorescence that they emit, just like Philippe Grangier did. And so now the idea was that we use this atom detection, have a computer quickly analyze the picture, and then say, look at just which traps are filled, which traps are not filled, turn off the traps that are not filled. And by adjusting the radio frequencies going into this acousto-optic deflector, we can move the traps that are filled containing the atoms into a new arrangement. And so I would like to show you what this looks like in this movie. So this might be an image. These are real atoms. These white dots are each a single individual rubidium atom. And so you can see here an initial loading where randomly some traps were loaded, some traps were not loaded. The computer then quickly analyzes this picture, turns off all the traps in the regions where no atoms are loaded, and moves the remaining traps to form a more compact pattern. And this movie has been slowed down by about a factor of 3 or so. In reality, it's about 3 times faster, on the order of 100 milliseconds. And so you can see that we can take these randomly filled things and then move them over. And most of the time, we get, a full pattern without any holes. Sometimes every now and a while, once in a while, you will see that, during transport, one atom was lost. For instance, here, one atom was lost, etc. So let's say in this position here, you can see that one atom was lost, etc. But basically, we could make these compact strings of atoms at over distances that we can optically resolve. So the distance between these traps is, I think in this picture, typically we work between 3 and 10 micrometers. This is probably 5 or so micrometers. So this is a picture of what is going on. We have, these randomly loaded traps, like in figure A, and then just by turning off the traps that have not been loaded and moving over the traps that have been loaded, we can make these strings of atoms, and they are of different length each time we try, because we load randomly, so sometimes we load more atoms, sometimes less. But we can also arrange the atoms in some other pattern. For instance, we can always have 2 atoms next to each other in 1D, or this is a picture of 10 atoms next to each other, etc. Okay, so basically this means we can, prepare the atoms. And just to show you, this is some early work, how efficient this is. If we didn't have feedback and we wanted to wait, to fill a 10 array size or a 20 array size just by waiting and having, randomly, succeeding, then this would scale exponentially. So it will take longer and longer to wait without the feedback. But if we rearrange of the traps at a time, we were able to load something like 60 traps. What is the minimum spacing between the atoms? That's a very good question. And how many frequencies and how are these frequencies generated? Good question. So the minimum size between the traps is set by the requirement that when, basically each direction here corresponds to a different frequency. And so when the traps start to overlap, also the difference frequency between 2 traps become closer and closer together, and so you get a beat note. So if the traps are too close together, then you get a beat note that is seen by the atoms, which acts as a force on the atoms, a modulation force on the atom that heats the atoms. So we find that when we go closer than about 0.5 megahertz or so in frequency, or corresponding to about 2.5 to 3 microns in distance, then we see a strong heating of the atoms because of the interference of the laser beams. As to how these frequencies are generated, basically we use a frequency synthesization arbitrary waveform generator to generate these different frequencies and then change them over time as we want to move the traps around. So these are radio frequencies, typically around 100 or 200, in the range of 100 to 200 megahertz. That are generating these different laser beams. And then basically we use computer control to turn off certain tones and then change certain other frequencies to move the atoms around. Basically the deflection angle of each beam is proportional to the frequency corresponding to that beam. By changing that frequency, we can change the position of the trap. Thank you for those questions. And so basically in 1D, you know, at that time we could do 60 atoms or so within 1 second, deterministically loaded. How do you ensure that the imaging the atom bonds in the trap do not disturb them? So it turns out, and this is also what Philippe Granger did, is you can image the atoms with, you know, MOT, with magneto-optically tuned laser light. You can image the atoms while they are in the trap, and they will not leave the trap. So the lifetime while being imaged is actually on the order of 10 seconds or so. In fact, the atoms live longer while they're being cooled and imaged than when we turn the trap off, and that's simply because we have laser cooling. So while the MOT light, magneto-optical trap light, is on, we have laser cooling, so the atoms, even if they're heated a little bit in the trap, they are cooled down again. So the lifetime during imaging is 10 seconds. What is the depth? So the AOD beams are the tweezer beams. In this experiment, each of these beams is the tweezer, the one generated by the AOD, and the typical depth, trap depth of each tweezer is maybe around 1 millikelvin or so. So that's the depth of the laser beams. Okay, and so you can see them fluoresce while they are being cooled. If we leave the atoms in the dark and don't cool them, then the lifetime is more like 1 second. Okay, so we have these optically addressable, resolvable atoms. We can space them separately. You know, we can image them, and they are several micrometers apart. And then the key question is, however, to make this really interesting, is can we make the atoms interact with one another over these optically resolvable distances? And here comes, you know, this idea of Rydberg blockade comes in about the same time as Philippe Granger imaged his single atoms around 2000. And, you know, the answer is obviously Rydberg, because with Rydberg states we can make interactions over optically resolvable distances. So we have the best of both worlds. We can individually control and prepare single atoms, and we can yes, so the spacing is fairly well controlled. Basically, the spacing uncertainty is given, well, there are two effects. One is, you know, how well can you control the radio frequency, because the radio frequency determines the angle. So the question was, I guess the spacing is not as well controlled as an optical lattice. So the answer is, you know, the radio frequency you can control rather well, but of course the confinement is not as tight as in an optical lattice. So, you know, when we are at a finite temperature, then the ground state size, or not ground state, but the size of the thermal cloud, or the thermal cloud of a single atom inside the tweezer, is certainly bigger than an optical lattice, but the Rydberg blockade radius is relatively large, exactly, so that we don't have a strong effect from, you know, thermal motion of the atom inside the trap. Okay, yes, the Rydberg blockade radius is very large. So, you know, how does this whole thing work? We, you know, space atoms in this example here by 10 micrometer or so, and then also, for instance, when we use this van der Waals interaction, C6 over R to the 6, if you go to a high enough quantum number, say n equals 70 or n equals 100, we can have, you know, megahertz type, megahertz strength interaction between atoms over this distance scale. So basically, when the atoms are in the ground state, they have no interactions at all. They are, you know, far apart. There are no collisions. They are not, you know, interacting with one another. But if one atom is excited and in the Rydberg state, and the other atom is still in the ground state, the interaction is also negligible. Ground Rydberg interaction is very weak. But when both atoms are, when we try to excite both atoms to the Rydberg state, then because of the Rydberg blockade, there's a strong energy shift on the order of megahertz or more. Maybe tens to 100 of megahertz, depending on the distance. Yeah, so here's the picture. If the atoms are further than the blockade radius, then you can excite them with a laser beam from the ground state to the Rydberg state. In practice, I have drawn just one laser beam. This is actually a 2-photon transition where we go off resonantly through an intermediate P state, very much like yesterday when I talked about EIT, but here we go off resonantly with a 2-photon transition from S, 5S in rubidium to 5P in rubidium to the Rydberg state. But schematically, I will just draw it into one arrow. And so we can excite the atoms from the Rydberg to the Rydberg state and back down. However, when the atoms are closer than the blockade radius, then the Rydberg-Rydberg interaction shifts the doubly occupied, doubly excited Rydberg state away from resonance. And so it means the atom, cannot be excited by that laser beam, and they will remain in the ground state predominantly. And then, for instance, if you have three atoms where neighboring atoms are within the blockade radius, but the first and the last atoms are not, then you can make excitations that are antiferromagnetic in character, where you excite the first atom. Because you excited the first atom, the middle atom cannot be excited because its Rydberg transition would be further away from resonance, like so. So the second atom remains in the ground state, but because the second atom is in the ground state, the third atom can again be excited to the Rydberg set, etc. So you get naturally some kind of antiferromagnetic ordering, or as I will show you, an Ising type interaction, a sigma Z interaction between next neighbors, or maybe more, depending on how many are within the blockade radius. So that's the picture for those more theoretically minded, or think of it in terms of Hamiltonian. Our Hamiltonian typically has three terms. Let's look at the middle, or the first term first is just this resonant drive. This omega of t is something we can control. That's basically the laser beam that makes the atom Rabi flop, sigma x Rabi flop from the ground state to the excited state back to the ground state, etc. So this term by itself on a single atom would cause Rabi flopping or spin rotations. If we identify the spin, with spin down being the ground state and spin up being the Rydberg state, then basically these are spin rotations induced by a laser, like a sigma x Hamiltonian. This term here, delta, is just the detuning of the laser. So if we drive the laser off resonance, then in a dressed atom picture, the ground state can be less energetic, or the excited state can be less energetic. So this is just a term associated with detuning from resonance, and the energy is just how many atoms are in the ground state versus the Rydberg state, the detuning delta. And then the interesting term is this Bij term, a next neighbor term, let's say, or next neighbor. So this basically is a energy cost if you want to excite two atoms to the Rydberg state. And typically we work in the so-called blockade regime, where this Vij is larger than all other energies in the problem, so that basically this makes it prohibitive to excite two atoms within a Rydberg blockade radius. And this is following up with the previous question, what makes the system relatively robust. So basically, if this term is large, and then there are small fluctuations in the Vij term because the atoms are at slightly different distances from one another due to thermal motion, let's say, it doesn't do very much. Okay, so then we proceeded to see whether we can see fundamental simple physics associated with this Hamiltonian. So for instance, we took a string of atoms that were spaced much further than the blockade radius. Let's see, there's a question here. Any tunneling in these potentials? No, the traps are very, very far apart, no tunneling whatsoever. We are talking about 2.9 microns. To get tunneling, you have to really go to optical distances, or to optical lattice distances of maybe 300 nanometers also. So you can think of the motion of the atoms pretty much being frozen out. They are in the trap, maybe they have some thermal motion, but no tunneling. These distances are way too large. Good question, Saikat. And so if we use individual atoms fast spaced, then each individual atoms can Rabi flop when we apply this laser beam from the ground state to the excited state, back to the ground state, etc. If we use a pair of atoms, like in the screen situation here, separated by 2.9 micrometers, which is much less than the blockade radius, then we see again Rabi flopping, but the Rabi flopping is faster compared to a single atom. And also we see only the excitation on one atom. So we never excite two atoms, because that would be far off resonance, because that costs a lot of energy to excite two Rydberg atoms. So we excite only one of the Rydberg atoms. But the square root of 2 simply comes from the symmetrization of the state quantum mechanically. What we're exciting from the ground state to the ground Rydberg plus Rydberg ground state. So we get a square root of 2. Or more naively, in a rate picture, you can simply say, if I have two atoms and I'm trying just to excite one to the excited state, well, in a rate picture, that should be twice faster, right? Because I can either excite the left atom or the right atom, so I get a factor of 2 in the rate limit, which is Rabi frequency squared. And that's the square root of 2 here. And similarly, for 3 atoms, we saw, root 3 enhancement in the Rabi flopping frequency between these states. Right, so this seems to work as advertised, and we have good suppression of 2 atom excitations. Now one can, turn this into some question about a phase transition or into a phase transition. One can start, say, this is now the horizontal axis, the tuning of the laser beam delta from resonance. One can start with all the atoms in the ground state, turn on the laser beam far away from resonance, it doesn't do anything, and then one can sweep the resonance, one can sweep the laser frequency through the atomic resonance, all the way to the blue side. And if you think of the ground state of the system, then on the left-hand side, it's basically the ground state is all atoms in the ground state, the GGGGG state. But then on the right-hand side, because you drove through resonance, the ground state is the situation where one Rydberg atom has been excited. The next atom next to it could not be excited because of this Rydberg blockade, so it remains in the ground state. Third atom is excited again, the fourth atom remains in the ground state, etc. So this is a Z2 type ordering, basically an antiferromagnetic ordering where every second atom is in the Rydberg state. And we perform all these experiments with odd atom numbers so that basically there's no degeneracy in the ground state. The ground state is the one on the right-hand side where the edge atoms have been excited to the Rydberg state, and then we have this antiferromagnetic pattern. If you used an even number of atoms, then there would be two possible degenerate ground states where the left or the right edge atom could be in the Rydberg state, and I'll come back to that later. So we basically expect this phase transition where we go from a disordered phase into this ordered antiferromagnetic phase. And if we put the atoms closer together so that not only next neighbors are within the Rydberg blockade radius, but second next neighbors, then we expect this Z3 ordered phase where every third atom is excited to the Rydberg state. Or, if you place them even closer together where every fourth atom is excited to the Rydberg state. And we could indeed see these patterns. So this shows you in a color plot where light color means Rydberg state and dark color means ground state as a function of the final detuning. So basically we ramp the detuning and then we stop at a certain value, and then we look at the probability of finding the atom in the ground or Rydberg state for a 13 atom array. And so we see in this characteristic Z2 order where every second atom is excited being evolved, or the Z3 order, or even the Z4 order, where every fourth atom is excited as we tune across resonance. So this is really a quantum phase transition driven by quantum fluctuations of the phase from one parameter to the other. So this is what it looks like, and we have also mapped out this phase boundary. Basically, we have looked at where does this order appear as we ramp, and we get good agreement with what we expect theoretically in terms of the two parameters detuning, where the phase transition occurs, and then the interaction energy, interaction rate. So basically, the larger the interaction range, we go from Z2 order to Z3 order to Z4 order, etc. And this is the picture. We are driving all atoms simultaneously with a laser beam, and then they arrange themselves in a certain distance. And so we can also look at the correlations between the atoms. So basically the correlations of, between atom I and atom J as a function of distance between them, where red means they are positively correlated, blue means they are negatively correlated. And then we see this characteristic antiferromagnetic correlation pattern where, this is the two order where every second atom is excited. And in these early experiments, we had already correlation lengths, not across the whole crystal, but of maybe 5 or 6, around 6 lattice sites. So if you take an average, Rydberg probability over the whole system, then for a 13 atom system, you see that the order is dominated by edge effects, basically because the true ground state is the edge atoms being excited to the Rydberg state, and then this kind of edge influences also what happens in the bulk. But for the larger systems, basically because we have kind of domain walls in this antiferrometric ordering, for the larger systems, inside this bulk here, the edge effects have dropped away, and we have, an average population near 1/2 of finding an atom in ground or Rydberg state, but we still have these strong correlations between neighboring atoms corresponding to these antiferromagnetic domains. Maybe one more thing, and then I will take some more questions that we observed that surprised us. So what we did here is we ramped across the phase transition first to create this antiferromagnetic ordering, and then we quickly quenched the system onto the onto the boundary, onto the phase transition boundary, basically to tuning at 0 or near 0. We quickly quenched the system, and then the idea was to observe whether we expected thermalization in the system. So basically, we develop the order, and then we quench the system suddenly there by tuning onto resonance, onto atomic resonance. And what we expected and what we wanted to study is, how the system evolves thermally. What is the thermalization time? We expected just thermalization because after the sudden quench, we can populate many, many states. So for instance, for 9 atoms, we have 2 to the 9 states. So we expected, some thermalization, but instead what we discovered was some oscillating pattern between 2 macroscopic antiferromagnetic states. So basically we saw an oscillation after the quench between the situation where the edge atoms were excited and the atoms next to that were in the ground state, to the opposite pattern where now the edge atoms were in the ground state and the next atoms were excited, and then back, which is, surprised us because remember, you can't excite a Rydberg atom next to another Rydberg atom. So before you can excite the second to last Rydberg atom, you have to de-excite the last Rydberg atom, but somehow the system has to remember what pattern it had before so that it can oscillate between these 2 states. So we saw these rather long-lived oscillations. So the question here is, how do you optically address many or all atoms by using several lasers? Very good question. So what we really haven't done so far, with one exception, is we haven't done really individual addressing far-reaching. I'll tell you a little bit what we did. But basically what we do is we take this whole string and then we shine a laser beam from the side, and the laser beam addresses all atoms at the same time. So far we have done only collective coupling here, where this Rabi frequency, as shown in this Hamiltonian, is the same for all the atoms. We haven't yet done full individual addressing, which can be done by individual laser beams. So here we drive all atoms, the whole system globally. Okay, so basically these are the oscillations that we saw after the quench. And now, surprisingly, these were very robust.
Vladan, I have a question. Yeah, so the thermalization curve you showed, so is this a finite size thermalization, as in do you have otherwise a reservoir in the background, or is it just this finite n atom, which is actually like the usual revival and coming back? And so
on. The usual revival and coming back, it's finite atom system. However, we saw these oscillations also for 51 atoms, right? So for 51 atoms, you have 2 to the 51 quantum states in principle. So there's a large number of states.
So from that oscillation, can you actually extract the number of atoms? Can you?
So it's not a number.
Usually the revivals depends on n, right?
Yeah. So these are not revivals. As you can see, so here's a comparison, the time after quench and then domain wall density, which basically tells you the ordering. And you can see that for 9 atoms and for 51 atoms, we observe what looks like the same oscillation frequency in the system. So it's not a revival. People think, in the meantime, theorists have been thinking about this. They call this quantum many-body scars. So it turns out that even in chaotic systems, you can have preferred trajectories in phase space. And it's believed that this is the generalization of that in a many-body. So that even though many states are in principle contributing, somehow the dominant states that are coupled have all this, this particular order. Right? So
there are some dark state kind of decodance-free subspaces which get separated out.
Yes, presumably that's what's going on, right? So if you look somehow at the density of states and energy, you would find that there are somehow groups. These are probably not single macroscopic states, but maybe groups of macroscopic states with very similar properties with this antiferromagnetic ordering that get separated. Yes, that must be what's going on. They are long-lived, but it's hard to model this. So I should also say, 2 to the 51, right? States that 10 to the 15 or so states. So basically, our ability to use direct, direct brute force diagonalization stops at about 25 atoms or so. That's partly why we chose 51.
Simulations tend to show for thermalization that 10 is a very large number, like 10, 15, 20. So maybe you're already in a thermal limit where revivals.
I believe so. You know, we've seen this with 50. I'll show you also later systems that we see it with 200 and also in 2 dimensions and so on. So this seems to be something, something, you know, fundamental and somewhat universal. So Mahesh asked, that is because every atom oscillates with different Rabi frequencies. Is it correct? No. So each atom, the Hamiltonian is symmetric. So each atom, or global, each atom will oscillate with the same Rabi frequency omega. So interestingly, the oscillations that we see here are not at omega, but at 1.55 omega or something like that. And so you could make a simple dimer model where you just took neighboring atoms, and then you would predict an oscillation at square root of 2 omega, which is close, but not, you know, definitely distinct from what we observe. And for instance, this paper by Papic, Serbin et al., they actually predict our oscillation frequency from a many-body model, from this kind of idea that you have groups of states that are separated. So it's a non-trivial effect in the sense that, for instance, you know, this oscillation is at 1.55 omega, where omega is the Rabi frequency, independent of the system size. So yeah, it seems to be a universal phenomenon. Okay, are there other questions about this?
No, there's nothing. You can go ahead.
Okay, that's something more in the chat. Let's see. Okay, all right, let's go ahead. So now we also investigated quantum gates. So here we just prepared 2 atoms, and then basically we used the Rydberg blockade to prepare basically a Bell state of the atoms by trying to excite 2 atoms. And so first we optimized our single qubit Rabi flopping. So we took a single atom, or many copies of a single atom. We first observed Rabi flopping like shown here, with maybe 10 to 20 oscillations. We found that our laser frequency noise contributed strongly, even though this laser was already stabilized to an ultra-stable low expansion cavity. But after improving the laser line width and using the light transmitted through the cavity and then amplifying that light, we could have single qubit Rabi flopping that was really, really respectable. And after many microseconds, we didn't see much decay of the system. We then placed 2 atoms next to each other and used this 2 Rydberg blockade to drive the system from the GG state, from the ground state, where both atoms are in the ground state, to the RG plus GR system state. So this is the symmetric state where either the left atom is excited or the right atom is excited. And we saw nice Rabi flopping between this GG state and this, if you want, is a Bell state. It's an RG plus GR. It's one of the Bell states. While we didn't see basically any excitation probability to the 2-atom Rydberg state due to blockade. And again, this shows you that the blockade is rather robust, and this was simply the energy scale is much larger than any variations of the blockade by motion, etc. So basically, we can drive the system from GG to RG plus GR and back down, and that allows us to, this deterministic preparation of the Bell state allows us to do quantum gates. So for instance, we can do this oscillation and then put in a phase shift on the atoms to demonstrate universal quantum gate. This is the probability distribution or density matrix for the 4 states. And we achieved a fidelity of, in 2018, of about 97% for the 2-qubit gate. And now in newer results, we have 99%. Why does the laser line width matter so critically? Well, it's a good question. This ground to Rydberg excitation is a quite narrow transition. And basically, if you want to keep the say coherence for 10 microseconds while you're Rabi flopping, then you need something on the order of less than 10 kilohertz or so laser line width. The experimentally observed sensitivity to laser line width was a little bit more than we expected. I mean, you can make a model and say, if you have phase fluctuation of your laser while you're driving, a single qubit from the ground to excited state, you expect this. It was a little bit larger than maybe we expected, but overall, it's just simple. If you want to, maintain the phase while you're flopping up and down, this is actually a 2-photon optical transition, right? So the laser line width matters on the kilohertz scale of both lasers. For the experts, we use a so-called inverted scheme, where we go from the 5s state, not to the 5p state, but to the 6p state with a blue photon, and then, sorry, with an infrared, with a blue photon, and then from the 6p state to the Rydberg state with an infrared photon at 1030 nanometer, just because, the matrix elements work out a little bit better there, and the available laser power as well. Right. And so basically this means that in, kind of a 2-qubit system, we can do, decent quality, decent fidelity 2-qubit gates, and we have also in the meantime tested other schemes that are not presenting that work a little bit better. But basically the short message is that we can use this Rydberg blockade to, in combination with individual addressing of the atoms, to make universal quantum gates between 2 atoms. Although the system is, as I will show you, good. The lifetime of the Rydberg atoms, yes. So if it was at temperature 0, you would expect maybe a millisecond, because the transitions to neighboring, we work here at n equals 70. So the transitions to neighboring states are at frequencies of a few gigahertz. So these modes are thermally populated at room temperature, and so the lifetime, the expected lifetime due to thermal excitations is about 100 microseconds or so. And the observed line with, in that corresponding range. Yes, Sourav. Okay, but the system, we are not really thinking at the moment so much of doing, digital quantum computing with it, because the system is really better suited in some way to do, many-body quantum gates, many-body state evolution and quantum simulation. So I would like to tell you about experiments where we created a quite large GHZ state system.
Vladan, there is a question.
Sure.
We need to stabilize ambient magnetic fields as well from Arijit.
Yes, in principle, yes. I mean, we don't go to any particular measures. We are not shielding the external magnetic field. Anybody who has been in Cambridge knows that both MIT and Harvard are quite close to a subway line that produces magnetic field fluctuations. So at the moment, these magnetic field fluctuations are more on the kilohertz to few kilohertz time scale, so they don't quite come in. So, but we certainly stabilize the current, but we don't go to extreme measures yet. But if we say wanted to improve the coherence times by another factor of 10 to 100, we would either need to stabilize the magnetic field. What we typically do is, as I will show you a little bit later, is we store the coherence in so-called clock states and magnetically insensitive states of the ground state when we're not driving to the Rydberg state. But it's a good remark as well. Magnetic field would matter. It doesn't quite matter because of the lifetime of the Rydberg states at the moment. Okay, so let's think about large GHZ states. So here the idea is that we are now going to, before I told you we had an odd number of atoms. Now we are doing an even number of atoms, and that means that there are 2 degenerate ground states in this antiferromagnetic ordering, right? Either the first atom can be in the Rydberg state and the second atom in the ground state, etc., or the opposite one. So we are trying to make a superposition of these 2 degenerate ground states, where either the leftmost atom is in the Rydberg state, and then we have perfect antiferromagnetic ordering, or the other way around. And of course, the big challenge, we know how that we can make this antiferromagnetic ordering. The big challenge is to maintain the phase between these 2 states, because this is a many-body phase that now will evolve n times as fast as a single atom phase in principle. And so this state should be in principle produced if we start in the ground state and then just adiabatically ramp to the Rydberg state, because these 2 states are degenerate. So ideally we should just prepare this degenerate superposition. However, what we found that when we did this is that we had edge effects. Basically, the edge atoms are special because they have only one neighbor, as opposed to all the other atoms that have 2 neighbors. So we have a complicated, I can't draw now, but basically we have a complicated many-body states as we tune our parameter, and there are states that come quite close to the ground state we want to prepare. So basically you can think of this, we have the ground state that we want to adiabatically prepare, and by ramping the laser beam on, we should go from GGGGG to this GHZ state, but then other states from above, other excited state, can come quite close with a small gap. And so the trick was to understand what these states look like by looking at simulations of smaller systems, and then use light shifts on individual atoms to shift these states away from resonance so that they don't come as close to the ground state. So here, for instance, this shows you for, I'm not sure how many atoms this was, probably 1, 2, 4, 6, 8, 10, 12, 14. So this was for 20 atoms, and where we adiabatically sweep, and then we list all 2 to the 20 states down here on the horizontal axis, and we see 2 states prominently come up. And the 2 states are really the 2 states, the ones that most prominently come up are the, one antiferromagnetic ordering and the other antiferromagnetic ordering. They come up most prominently, far more prominently than any other state. And then there are a few other states that maybe you can see down here appearing every once in a while. And then to achieve that and to basically move, the states that the system can go to that we don't want via a diabatic and non-adiabatic transition out of resonance, we found that it was useful to apply light shifts onto the edge atoms. And then it turns out, to next order, it also helped to apply light shift onto selected atoms next to the edge atom, because once the edge atom is out of the picture, then the other atoms matter. So it turned out that it was most, from calculations, we figured this out in smaller systems, it was most useful to apply also some light shift onto this atom. And what this allowed us to do is basically tailor the many body spectrum in such a way that we would have fewer of these non-adiabatic transitions as we ramp the ground system parameter. And already for 20 atoms, we have, 1 million states, and we were populating essentially only 2 of those million states. And then when we looked at the density-density correlations, now we had nice correlations across the whole 20 atom array that basically were, which parameters to scan to observe these 2 GHZ states. So yes, so basically we scanned across we did the same thing as we did here. We scanned across the quantum phase transition. So basically we did this scan, or maybe just this scan here. We just did this scan here in a Z2 ordered system, sorry. We scanned the detuning in a Z2 ordered system. The only difference with these early experiments was, instead of having an odd number of atoms where the ground state is unique, where always the edge atoms are Rydberg atoms, we used an even number of atoms where the ground state has these 2 possibilities. Does this make sense? So we just scanned basically that one parameter, the detuning, but then what we did to optimize this population and these correlations is we adjusted the intensities. We basically put light shifts via external laser beams, and here we had individual addressing. We put light shifts onto the edge atoms as shown here, and then also on to some other atoms near the edge as shown here, to basically shift some of the many body states away from resonance. And then we saw these, very nice correlations of the system, density-density correlations, which persisted over the whole, 20 atom 1D crystal. And then, but we want to, of course, know not only whether we have prepared a mixture of these 2 states, but whether we have actually prepared a coherent superposition between these 2 states. And for that, we can modify this phase e to the I5, so we can apply light shift on every second atom, which will shift the phase of this state, but not of this state, if the light shift acts only on the ground state. So basically, if we apply the light shift only on the ground state of every second atom, then this right state will be shifted in energy, this state will be not, so there will be an overall phase shift in these 2 states. And so when we did this phase versus phase per atom, we saw these nice fringes as a function of the phase. And for 4 atoms, you see, so the phase was shifted from -pi to pi over 2pi. For 4 atoms, we see the fringes move. When we have more atoms, because it's a many-body phase, the fringes move faster, and we could see fringes with a contrast bigger than 1/2, which would be the classical limit, all the way up to 20 atoms. So up to 20 atoms, we could basically verify that we had a quantum superposition of, or equivalently a GHZ state, a quantum superposition of these 2 microscopically distinct states in the system, which was a record at the time. Soon the superconducting qubit people also got to 20. They may have exceeded that number by a little bit, but the record is around 20 or so at a time, interestingly, in several different systems. So here, already in 2011, Rainer Blatt's group made such GSD state with a different method in a 14-ion crystal, and then at the time of our publication, 2018, the superconducting qubits were at 18. I think they are now maybe also this system. So is it possible to create Z free from the ground state? In principle, it should be possible. We didn't try to make these states for the even atom number, but it's, we did make them, as I said, the Z free and Z free ordered phases via evolution from the ground state for odd atom number. So they were not GHZ states, but basically these experimental results here, this uppermost system here on the right shows a Z4 ordered state and a Z3 ordered state. And I will show you a little bit more when I talk about basically the Kibble-Zurek mechanism in sweeps. Yes, so it's possible to make Z3 states. We didn't try to make Z3 type GHZ states in the system yet. Okay, now we can, investigate, the so-called quantum Kibble-Zurek mechanism, or what happens as we sweep across the phase transition. So as I showed you before, when we had a 51 atom system, we had only a coherence length, which was not the full crystal, not 51, but only on the order of 7 or so. And then we have a domain wall, and then we had another, domain, etc. And it turns out this was limited by our preparation speed. Basically, the Rydberg atoms live only for a certain time, and also they tend to fly away because the Rydberg atoms are not trapped in dipole trap, unfortunately. In fact, they are anti-trapped, so we do all these experiments. After preparing the atoms, we turn off the traps, and then we drive the system quickly. So we found that our coherence length was limited by our preparation time. The slower we ramped, the better we did in the system. And that's basically because at finite ramping speed, you have transitions to many body states which are, away from the ground state, but which have a finite gap. So we investigated, how basically these domain walls, how often they occurred when we did things. So this shows you, for instance, an example. If we start with this arrangement of atoms and try to make this antiferromagnetic order, then we see two types of defects. The more common type of defect is where, two atoms, neighboring atoms are in the ground state. So here red circles indicates Rydberg states, and the green dot indicate ground state. So we find more often these errors where, an atom should have been excited to the Rydberg state, but it wasn't. So neighboring ground state atoms. Every once in a while we find two excited Rydberg atoms, but that's much rare because there's a large energy cost associated with it. Here's an example. This is probably not really an excited Rydberg atom, but the way we detect the Rydberg atoms is we blow away the Rydberg atoms and then we look at the remaining ground state atoms. So loss of atoms from the system also appears to us as if it was in a Rydberg state. So in this system, more likely actually this atom was lost rather than that it was really that three neighboring atoms were excited to a Rydberg state. What creates a defect is a control 2. So as I will show you, the creation of the defect is given by the ramping speed. The slower we ramp, the less defects we have, and the other way around, the faster we ramp, the more defects we have. You can think of it in the following way. I think I have a graph for this. That as so you have some kind of critical point that separates the phase 1 from the phase 2. So the phase 1 in our case is this GGGG disordered phase, and then the phase 2 is this ordered antiferromagnetic phase, and there's a critical point associated with it. And then basically as we ramp, through the critical point at a finite speed, then at some point, basically you need a certain time to make correlations, and to make larger correlations over a bigger system, you need more time. And if you ramp too fast across this transition, then basically, the crystal on the antiferromagnetic crystal on the left didn't have time to communicate with the antiferromagnetic crystal on the right, and so there will be a chance of a domain wall forming between them. And so this so-called Kibble-Zurek theory that was developed originally in another context applies also to these quantum phase transitions. And basically it relates, the time that it needs to form the phase. It relates it to the distance from the critical point. So you have this critical point, which, for instance, in our, this G parameter for us is the tuning that we are ramping, and so it relates the the measure. There's a predicted relation between the density of domain walls, how often we have errors in our system, the density of domain walls, to how fast we ramp in the system. And basically, at finite sweep rate, random phase boundaries appear because at some point the sweep time is faster than the equilibration time over the whole system. And so the faster we sweep, the more on average density of domain walls we expect. So this shows an example where we swept fast on the top row and we had more domain walls. So red and gray are different domains with domain walls in between. And then when we swept slower, we had fewer domain walls happening in the system. So we investigated the correlation length, which is 1 over the number of domain walls as a function of the inverse sweep rate. And we can use it to extract the critical exponent. So basically, the slower we sweep, the longer correlation length we expect. We try to vary this over a wide range as possible within limitations, because of course we have the boundaries. So, at some point our crystal approaches the whole length, and then we don't have meaningful measurements from the bulk anymore. Nonetheless, we could, fit critical exponents to it. And the critical exponent that we expected, 0.5, is the one that is also known 1/2 this critical exponent for the Z2 order. We did also simulations with matrix product states shown in red here, which agreed well with the experiment as well. So for the Z2 phase, the situation was rather simple, and we can see this critical exponent. The Z3 phase, for instance, things become more complicated, because for the Z3 phase, we can have 2 different types of errors. We can basically have errors that make it look more like the Z2 phase. So this is something inside the Z3 phase. So remember that we varied the Z3 phase by changing the blockade radius relative to or changing the distance between the atoms relative to the blockade radius. So here, for instance, you see that we have a Z3 phase, 1 atom Rydberg, 2 ground, 1 Rydberg, 2 ground. And then we have here a little bit of a Z2 phase where we have Rydberg, ground, Rydberg. So this would correspond to Z2 phase. So this is closer to Z2, where the dominant effects are of this type, where we have basically an interstitious thrown in Z2 phase. But if we vary the parameter, make the blockade radius larger relative to this system distance, then we see more of these type of effects where we basically have a Z3 phase with errors of the Z4 phase type thrown in. And we found that which type of defects occurs changes with this ratio of atomic distance to blockade radius as expected. So let me see, there's a question here. We think not. So we didn't really test it both ways. That's a very good question, because the phase 1, which is all atoms in the ground state, we can prepare with with unity fidelity essentially. But the phase 2, where we start with this antiferromagnetic order, we cannot prepare it that well. So if we try to prepare it, we already built errors into the system. The expectation, I think, is, I believe, that the critical exponents do not depend on which way you go across the phase transition. But I must say we didn't check it experimentally, simply because we cannot prepare the Z2 phase so reliably as the other phase. And so here, for instance, as a function of interaction range RB over A, we plot on the vertical axis the scaling exponent extracted from the data. So basically we take data like this here, where we look at the correlation length versus the sweep time, then fit the exponent, and then do this for different ratios of RB over A, blockade radius over distance. And so what we see is, for the Z2 phase, for instance, we see a clear plateau in a certain interaction range, and the dashed line is the predicted value of 1/2, which within errors we observe. For Z3 and Z4 phase, we don't actually have reliable knowledge of what critical exponents are. There are some finite size metric product state calculations, for instance, that predict these errors, but they are not really known from theory reliably. And so we can see that the critical exponent varies near the phase boundaries when there's a competition between Z2 and Z3 phase, and then there seem to be regions where it's relatively flat, where it plateaus. So we identify this as the critical exponent for the Z3 phase, which you see is different from the Z2 phase, and for the Z4 phase, which is again different from the Z2 phase. Right, and then in between, more complicated things are going on, where there's a competition between two different orders. And this slide is maybe just to show you that, because we can image all atoms, we can look at the various possible defects. And so we can see, for instance, that, when we start sweeping, we have overwhelming probability to be in the GGG state. And then, that probability disappears, and then, across the phase transition, different states are populated in a temporary way, and then finally we arrive with high probability in this ordered, antiferromagnetically ordered states RG, RG, R. But you can see here, this goes back also to quantum many-body scars. Here in the region of the quantum phase transition, actually many different states are populated while this transition forms. Okay, so this was all experiments done on one-dimensional arrays. Are there more arrays? Are there more questions about this? Isn't the scaling dominated by finite size effects here? So there's a limit on it. Basically, that's why, go back to here. So we worked up with 50 atoms in the crystal. So here you can see, for instance, the correlation length is up to 4. So if we think that, when the correlation length is up to 4 or so, then out of such a long crystal, that edge effects don't really matter. One way that we excluded edge effects is we didn't look actually at the first 5 atoms or so on the left or on the right. We excluded those from our analysis. We looked just at the atoms inside the bulk. Where edge effects had, we think, died out. If I remind you here, when we looked at these crystals over here, you can see that the edge effects, are maybe prevalent up to 7 or 8 atoms, and then they seem to have died out. So we didn't look in the analysis at the edge atoms. We looked just at the atoms in the bulk, but still, you're right, it limited us on how long correlation lengths we could look at, because, once they became longer, they were simply dominated by edge effects. So that limited the dynamic range. Ideally, you would want to change this over an even much larger range, at least an order of magnitude or so, to have more reliable critical coefficients. Thank you, Saikat. Okay, now I would like to tell you about two-dimensional arrays. We have a little bit of time left. So two-dimensional arrays are harder to arrange, but we manage now to do two-dimensional arrays. I'll show you a movie. So this is now I forget now, 20 by 40 or something trap sites in 2 dimensions, and then we rearrange them, and we get almost perfect with a few holes here, 2-dimensional patterns. And I think I have a movie showing, we run this with different arrangements. So we randomly load, the computer looks at the picture and then rearranges the atoms. And the atoms down here are the atoms that are left over when we arrange this pattern. So in 1D, it was rather easy. We could just use the AOD for sorting. In 2 dimensions, you cannot use crossed AODs because you need to do each trap. You cannot use crossed AODs directly because you need to have access to each trap. So what we do is here we have a stationary pattern of traps that we make for the experts by a spatial light modulator. Makes a stationary pattern of traps, and then we have an acousto-optic deflector that moves the atoms in the vertical direction. So basically we look at each column here, and then we have basically we have a sorting system which looks at each column and then basically compresses each column in the vertical direction, similar to the way that we did with the acousto-optic deflector. So each column is compressed in the vertical direction, and then afterwards we have some atoms left that were not used to form the pattern. So this sorting takes now a little bit longer, but not too much. It takes us between 100 and 200 milliseconds. to sort and place these atoms into the array. However, we start already to be limited by the lifetime. The lifetime of the atoms is about 10 seconds for us, but if you think of sorting, if you think of sorting 100 atoms in 100 milliseconds, then on average you expect already to lose one of the 100 atoms, even if your lifetime is 100 times longer than your sorting time. So even if for a lifetime of 100 seconds and a sorting time of 100 milliseconds, on average we lose one atom. But so this is, we get a filling fraction of about 98%. And yes, Sourav, I would say this is like magic. If you had asked me, 5 years ago, is this possible? Then I would have, I would not have seen it maybe before 2016. But right now, the largest pattern that we have made, as I will show you, are already 256 atoms, and we're hoping to push it much further. You may know that, for instance, Google's Sycamore processor worked with 52 qubits, and the ion trap group of Chris Monroe was also working with 52 qubits. This was basically, we did this 51 atom work that we published in 2018, and we chose just 51 so that it was bigger than 25 atoms or so, which you could still directly diagonalize. But now, we have pushed, and then all the superconducting qubits and the ion traps, reproduce that number. So we are very curious whether they can scale up to 250 qubits. So Saikat, you're asking what are the errors? So the errors are, one definite contribution is this lifetime. So the lifetime, as I said, of the atoms in the trap while being cooled and transported is 10 seconds, but it takes us about 100 milliseconds to load. So we expect already 1 of 100 atoms to be lost. And that explains the filling fraction. To make this a little bit better, what we do is we sort the atoms, then we look at the picture, and if we see holes, then we try to fill the holes. Afterwards, and that's a little bit more robust and allows us to increase the fraction a little bit beyond the lifetime. But we think in the future, it will be more important maybe to increase the lifetime by a factor of 10, and maybe also try to make the sorting faster. Okay, so we have now these 2D systems, and I should say, well, 1D systems, antiferromagnetic systems, IACS model are pretty well understood. 2D systems are not. And we can also sort into different patterns. So here I'm showing it, maybe it's a little bit small, I hope you can see it. We can, load the atoms and then rearrange them into either a rectangular pattern, or down here is shown as a Kagome lattice pattern. We have also here a triangular lattice pattern under D. So basically we can prepare the atoms and various lattices of our choosing, and even random lattices. And then we turn on the Rydberg interactions, and then, for instance, in the 2D lattice we see this antiferromagnetic 2D ordering, and I will also show you a little bit of results on orderings in frustrated systems like the triangle lattice and the Kagome lattice, where you actually have frustration, because if you have 3 neighbors, and then if one spin gets excited, then you don't know which one of these possible states is occupied. Okay, so that's what we can do in 2D. So here's some results for a 2D lattice, where we change the spacing between the atoms relative to the blockade radius. And so if in the simplest situation, which would be like the Z2 order in 2D, where basically the blockade radius is just the 4 next neighbors, then we see this nice and very simple checkerboard pattern or chessboard pattern, right, where one Rydberg atom is accompanied by 4 next neighbor ground state atoms, and then diagonally we have Rydberg atoms. When we increase the blockade radius so that the blockade includes not only, or this one for not only the next neighbors, but also, go ahead.
Yeah, there's a question that when you use the there's a question from Mahesh that when you use the AOM and when you use the SLM, that's not very clear.
Oh, so I see.
Just to take
okay. Yeah, so but basically what we do is we project. I wish I could draw somehow. The drawing function is turned off here. But basically we have this station. So the spatial light modulator can produce easily patterns in 2D, but it cannot change them quickly. Okay, so the so-called spatial light modulator is basically a spatially varying faceplate. It can make a pattern, but the pattern is stationary. We cannot move it. And then in order to move the atoms, we use the acousto-optic deflector, which can move traps, but only works in 1 dimension. And so basically what we have is the pattern is projected already spatially fixed pattern is projected of traps. And then on top of that, we turn on movable tweezers with the acousto-optic deflector. And so basically we pick up an atom with an acousto-optic deflector tweezer, which is deeper than the trap for the spatial pattern. We move it across the spatial patterns to a new location, and then we drop it there by turning off the acousto-optic deflector. Is that a little bit clearer?
Yeah, but how long is the loading time? Like, do you have a issue with how efficient is the loading?
So this would be a typical loading into the static pattern. The picture here on the B under load. That takes about 100 to 200 milliseconds to load, on the average half of the traps into this pattern. And then we now turn on these acousto-optic deflectors, which are deeper tweezer traps that can be moved, but only along the vertical direction. And then basically we compress. You can think of this as n times the one-dimensional system, where we now pick each atom. We pick, say, this atom and move it 1 over, and then we pick up this atom and move it 10 sides over, and this atom and move it 12 sides over. But we do everything in parallel to be faster. And this whole thing in our best system that we have found so far takes about 100 milliseconds. Yes, so there are 2 different beam paths that are superimposed for the AOD and SLM. Here it's shown. So basically the SLM is projecting the static picture, and then on top of that we have the AOD with these movable traps, and we make the AOD traps deeper so that we can pull out an atom out of a static trap and move it to another static trap. Hopefully that clears it up.
You can go ahead.
Yeah, but it still takes 100 or 150 milliseconds or so. Okay, so I was showing you some patterns that emerge. So in 2D, the situation is much richer, even in a square lattice. So for instance, at some point you can get this order which is not symmetric, along the vertical, along the horizontal axis, where you kind of, along the basically you have these rows of ground state atoms that separate. This is the ground state also calculated or expected for this larger blockade radius. And then for an even larger blockade radius, you get another order here, which is again not symmetric with respect to X and Y. As you can see, it has kind of, this 3 ground state atoms next to each other horizontally, but only 1 ground state atom next to each other vertically together with these rows. But in any case, we find that we see in these geometries what we expect theoretically for the ground state for various interaction strength in the lattice. It becomes even more interesting in this hexagonal geometry and the triangular geometry. And we have now a correlation length which is 11 sides along each direction in 2D, which means that you have already, for 120 or so, 120 11 by 11 array would be entirely entangled, and even this largest, 16 by 16 array is almost fully coherent along both directions, right? So 11 out of 16 atoms are entangled with each other. So we're making progress, to making fully coherent systems in 2D. So one thing that we studied is these quantum many-body scars, these oscillations after the quench. And we found that already what we saw in 1D, that they are quite robust even in 2D.
Sorry, I couldn't hear what you said.
Sorry, somehow my Siri turned on. Apologize. Okay. We see these quantum many-body scars robustly emerge in various lattice geometries. We tried, 1D chains as before, squares, honeycombs, Lieb lattices, decorated honeycomb lattices, etc. And in all of these, after the quench, we saw robust oscillations. And if some lattices had more robust oscillations than others, so it's something interesting to understand in terms of the many-body spectrum. And we also found that if we drove these lattices, these oscillations, we could actually stabilize these oscillations longer by driving them. So the one question was, how do we characterize the entanglement? So what we do is we look at the correlation length. I don't have now. Basically, we look at these correlation functions like we did in 1D. So we look at correlation functions like this one here shown on the left here in 2D. And then we look at how they die off versus distance. And then, we determine the 1 over E time or 1 over E length of these correlations to die off. And then we say, well, inside this correlation length, the system is more or less fully entangled. And so the dream here in this system, this was a 1D system where we had, correlations that were, 20 atoms in 1D long. Yeah, so it's an entanglement witness, if you want, a very simple one. We haven't really done full entanglement, I should say, because you should measure something else. So it's more like an indication of, a rough indication of the quantum coherence in the system, right? We have to think more carefully how to, what we would need to measure to really quantify entanglement over large distances. As a final thing I would like to show you is probing topological spin liquids on a Kagome lattice. So here we arrange the atoms. I hope you can see it. It's a little bit small on a Kagome lattice where you arrange the atoms on the links of this lattice. So the green dots are the atoms, and they are arranged so that there's 3 atoms in close proximity to one another, as you can see. And we can arrange the blockade radius so that the 3 closest atoms are fully blockaded, but that there's also an effect on the next 6 atoms away from these 3 atoms, as shown in this picture B. So basically what we expect is that on each of these 3 atom sublattice or subunit, we expect to have just one Rydberg atom, but which atom is excited is, completely random, or could be any of these 3 atoms. But then there's also some interaction between which pattern you choose on one sublattice, on one side, this 3 atom side, and which excitation you choose on another sublattice side. So we can make, in this situation, a dimer model where there are many different possibilities to populate this lattice. So we know that out of the 3 next neighbors, only one will be excited, but then there are, given one pattern here, one of the atoms, there's many different possibilities how the next system can be excited. The energetically most favorable state is the one shown in this circle, where basically if this red Rydberg atom is excited, then it has, 2 close next neighbors here, these 2 and these 2, and these are preferably in the ground state. And then that fixes this red atoms to be excited here of the next pair, but the Rydberg blockade radius is less than, say, in this direction. So in this new unit here, over here, hopefully you can see my mouse, we can choose which one of these 3 atoms is excited freely. And so we expect in this system the ground state to be a spin liquid, where you have many different, possible ways of arranging these atoms so that they fill the whole lattice and satisfy this blockade criterion. So we believe that the true ground state of the system should be, these various different lattice or superposition of all these various different lattice orderings, right? And not just the mixture. And so to identify whether there's any topological structures, we can go around loops and then associate, a certain characteristic parameter with the loop. So yes, we see frustration. Yes, so you can think of this as frustration. Yes, we do see frustration in the system Saikat. So we see many different orderings between the systems when we repeat this experiment, and we see also some kind of coherence around the loops. So basically, we can kind of go around this loop, and then we define a certain parameter here that is either +1, 1, or -1, depending on which atom on this little loop is excited, which of these 3 atoms as we go around the loop is excited, and we can quantify this parameter. And we see that this parameter going around these various loops is non-zero as we, is non-zero as we create this, what we think approaches a spin liquid phase, in any case, a frustrated phase in the system. And so we can define a parameter that kind of just, measures how the atoms are oriented along the z-axis to one another, which atom is spin up, which atom is spin down. And we can also, via quench, try to measure an x parameter, which roughly speaking measures the coherence in the system between these loops. So in short, we see both, z parameter as we go around these loops, and the x parameter coherence that we can measure by quenching the system. So in short, we think that on these systems we have some evidence that we have prepared not only a mixture of these different frustrated orderings, but also have a relative phase between at least some of these states in a state that approaches what we expect of a quantum spin liquid, which is many different possible frustrated orderings in this system. So maybe that brings me to the end. My class, I'm a little bit hoarse also. So where do we think we can go in the future? What I've shown you was 256 qubits. We think that we can go to 300 to 1,000 qubits in 2 dimensions within the next 1 or 2 years. At that point, we start to be limited also by laser power. Each of these traps consumes between 1 and 10 milliwatt of laser light. So, with the 10-watt laser, we can make around 1,000 traps. Beyond that, we have to think. Also, sorting these large arrays will start to be a problem, although we think we can improve the lifetime and maybe the sorting speed a little bit. We have done already 2 arrangements. One can also do 3D arrangements, but it's much less clear how to address atoms in 3D. But I should point out that Antoine Brouvet's group has done 3D arrangements in these systems. And in any case, we have, I think, an exciting prospect to study strongly interacting spin models, including, frustrated models, etc. What we haven't done really is local addressing. So far we have done everything globally with the exception of the GHZ states where we introduce light shifts on selected atoms. But one of the problems to solve experimentally for large systems is we would like to have ultimately individual control of the energy and the Rabi frequency of each atom. And we are working on that. And then I think, the really one very interesting question, we have no doubts that this will be useful to, simulate quantum systems and physics, but we are really interested whether this, method can be used to find solutions to hard classical calculations. So can we use adiabatic evolution to find, for instance, an answer to a traveling salesman problem or one of these recurrent problems in a way that scales differently than classical computers. And at this point, I would like to stop and take your questions. Thank you.
Saikat?
Yeah. Vladan, so I think I missed the liquid part. How is it a spin liquid in the sense that you still have a local, long range ordering? No?
Well, we don't have, we have, what should I say, long range ordering. So each time we do the experiment, we see a different arrangement of which, these plaquettes here, these little dimers here indicate which Rydberg atom of the 3 is excited. Right? So each time we repeat the experiment, we have a different ordering of these dimers, and there are exponentially many orderings of these dimers, right? So that just says that, when we do a single experiment, we are either in this state or that state or that state or that state. And then now what we're trying to see is whether there's a coherence between these different states, and that would indicate a spin liquid, right? So what we can do is we can do something which is equivalent in a many-body sense to sigma x measurement, right? If you want to prove entanglement, right, you want to measure along 2 different bases, right? Sigma c and then sigma x. So we think we have a witness that measures the sigma x entanglement, which we achieve by a quench. So we can only measure sigma z, unfortunately, but we can measure a sigma x or an x parameter by quenching and then rotating, so to speak, x. It's not a perfect rotation, but it's an approximate rotation of this x parameter. And then to our entanglement witness is whether when we go around different loops, and we define some kind of parity just by looking at how many dimers we find going around the loop, right? Then when we average over all different loops, is this average 0 or is this average non-zero? Right? And that tells us about the coherence of the system. This system is completely coherent, and average over all loops, sometimes you would find an even number of Rydberg atoms, sometimes you would find an odd number of Rydberg atoms, right? And that would tell us that these systems are completely independent. But what we see is even for bigger and bigger loops, as shown here, we see that this parameter is non-zero. which basically, if this orange parameter is really non-zero within the error bars, it tells you that you have some kind of quantum coherence or along this loop, right? That there's not the domain
kind
wall.
of scars also. There's same scars you were talking about earlier.
Exactly. It's both scars and it's also just domain walls. You can think of, there's some ordering and then a domain wall and then another ordering. And this teaches you something about the density of domain walls in this 2D system.
So the question is, the million-dollar question is, can you actually draw the phase diagram for the system? Or is it something special with the Kagome lattice that you always get a liquid?
So I believe that theoretically it's not, proven, but it's strongly believed that the ground state of this system is spin liquid, and finite size calculations also indicate that. Right.
So you will always have a liquid.
So it's believed that the ground state is a spin liquid for this lattice. But nobody has really observed it. Go ahead.
Yeah, so another general question I had for this kind of systems that, of course, like Google is talking about 51 or 50s-bit quantum computer. It's a very general question that, do you think that really, like when a full-blown quantum computer comes in, there is also this question, since you have been interested in this for a long time, that, like if you start having like 1,000 qubits or 1,000,000 qubits, that's effectively starts becoming a classical system. So actually a quantum computer is a, is really like eventually something will conspire to make it classical, or do you think that there will be still for 1,000,000 qubits, we'll see quantum effects?
Well, if we can implement error correction, right, then in principle, even 1,000,000 qubits should be, a quantum system. Now, nobody has really shown error correction in the sense that it lengthens the lifetime of quantum state substantially or even to infinity, right? So the big question is whether we can implement error correction, and error correction is just very hard to implement, and it requires very large overhead. You need many physical qubit copies to it, one qubit, and you need many operations. My feeling is that one should first push on the fidelity as far as one can without error correction, and that will make error correction simpler. That being said, these 250 atom systems we already cannot calculate, right? If we have full coherence across the system, it should allow, it is a quantum system and not a classical system, and so. I believe that it is different. I think the bigger question is it useful? Is this quantum system useful for classical calculations? But I have no doubt that already the quantum system is much richer than the classical system. It's not classical.
Yeah, I was asking something more simple, that whether you expect that with larger n scaling, there's a transition from classicality to from quantum to classical. Actually.
Fundamentally, no. Fundamentally, I think with error correction, people have shown that this can be fixed. Whether in practice, with finite quality of operations, whether it will be achieved, that's a different question. So, do I believe we will have fully quantum systems? Quantum computers sometime? I believe so. I think human ingenuity. Will solve this problem as well. When it will happen and which system it will happen, I don't know. But that's one question. The other question is already, systems like we have, like quantum simulator systems that have finite errors, are they already? I wanted to ask also this question. There was something about aberration. And so, yes, we have different trap depths. So we image the trap depth, and then we have a feedback algorithm which, modifies the SLM phases and optimizes numerically to make the traps, similar depth. So the traps are within 1% of one another in trap depth. And again, because we are using always the blockade, we are somewhat robust to the local temperature of the atom or the local trap, because we are not using typically the absolute value of the interactions. We're just using an interaction that pushes the state far out. But of course, when we do the adiabatic evolution, then small energy differences do matter. And so at some point, we are probably will be also trapped. At the moment, we are more limited by temperature of the atmosphere, not yet cooled to the ground.
Vladan, so thanks a lot for your extremely nice talks, and this also happens to be the last talk of the school.
Thank you very much. It was a great pleasure, and thank you for asking so many questions. It makes it much more fun to interact.
Yeah.
Okay,
thank
bye
you.
bye.
Okay.
Thank you.
Thank you. Bye.
Good night. Yeah,
Good
and
night.
have a good day. Yeah.